and welcome to this, the 11th Clarendon Lecture in Finance. It's a series that's run by Oxford University Press. Very, very grateful to Adam Swallow, who's here for having organised this lecture. And actually the originator of the lecture series, Andrew Schuler, is also with us this evening, so it's very good to have him here with us as well. We've had a dazzling star of speakers during these lecture series, starting off with Michael Brennan in 2002, and most recently having Peter DeMarzo as a lecturer here. This evening, we're particularly fortunate in having an exceptionally distinguished speaker with us, Andrew Lowe, who's perhaps done some of the most interesting and significant work in the area of asset pricing, rationality, and behavioural finance and institutional finance. He's the Charles and Susan Harris Professor of Finance at MIT. He is the Director of the Financial Engineering Lab at MIT. He's also the founder of a very successful investment management firm called Alpha Simplex, which has made some important innovations in the field of asset pricing and behavioural finance. He's an author of numerous extremely important articles in the field. He's an editor of many finance journals, the winner of numerous prizes in finance. He's a graduate of Yale and came out of the doctoral program at Harvard University in 1984. And above all, he's a remarkable mind, a tremendously interesting and pleasant person to interact with, a fantastically good lecturer. And so we're really in for a tremendous treat today, and it's a fantastic pleasure for me to be able to introduce Andrew for tonight's Clarendon lecture. Thank you very much.
I'd like to start by thanking Colin for that very generous introduction. I'm a little worried now because I think that they can only go down from here. We have to reduce expectations, not to raise them. I also want to thank Oxford University Press and the Saïd Business School for inviting me to deliver the Clarendon Lectures for 2013. It's an extraordinary honor for me to be included among the impressive list of Clarendon lecturers, not just in finance, but in other fields, including economics, English, law, and management studies. And I have to say that I'm especially pleased to be delivering these lectures at the Saïd Business School because as a 15-year-old institution in an 800-year-old university, it's a fascinating kind of complex of old and new that I think is very much along the lines of the topic that I want to speak of for the next 3 lectures. In fact, if Edward Hyde, the first Earl of Clarendon, were here today, I think he'd approve of the Clarendon Lectures in Finance, even though that's the newest among the lecture series. Because as many of you probably know, Lord Clarendon was at one point, very briefly, the Chancellor of the Exchequer. So finance is certainly a subject that was near and dear to his heart. I think he would also approve of the topic that I'm going to be covering, the role of human behavior in financial markets, because as a politician who earned the love as well as the ire of his king when he was Lord Chancellor and Chief Minister to Charles II, I think he'd understand and was a keen student of human psychology. And so I think what we're going to talk about today are subjects that were very familiar to him. I want to start with this notion of human behavior. And it's a notion that I think all of us are familiar with, but economists have a particular view on. And that view was really informed by 2 leading schools of thought that ultimately merged into one theory of economic behavior. And I'm talking, of course, of the theory of expected utility. Paul Samuelson, in 1947, in his PhD thesis, outlined the basic principles of utility theory. And his PhD thesis was very modestly titled Foundations of Economic Analysis. Now remember, he was a PhD student. And the fact is that it was modest because it did become, for our field, the foundations of economic analysis. Every first-year PhD student in economics and finance will learn the basic principles of revealed preference, of maximization of utility subject to budget constraint, and of course, around the same time, von Neumann and Morgenstern, in their theory of games and economic behavior, extended that axiomatic approach to the case of random payoffs, to the theory of expected utility, maximization of the expected value of a concave objective function subject to a budget constraint. It's an interesting fact that in the field of economics, this is the only theory of behavior that we teach our students. And I say that with great emphasis because psychologists are extremely jealous, believe it or not, of economists because they have many, many theories of human behavior, whereas we have just one. And you understand, of course, that there may be some limitations to that theory. But before we get into that, let me tell you what Paul Samuelson wrote in 1998 when he described how he came upon foundations, what he was trying to do in his PhD thesis. So let me read to you what Paul Samuelson wrote in 1998. Perhaps the most relevant of all for the genesis of foundations, Edwin Bidwell Wilson was at Harvard. Wilson was the great Willard Gibbs' last and essentially only protege at Yale. He was a mathematician, a mathematical physicist, a mathematical statistician, a mathematical economist, a polymath who had done first-class work in many fields of the natural and social sciences. I was perhaps his only disciple. I was vaccinated early to understand that economics and physics could share the same formal mathematical theorems, Euler's theorem on homogeneous functions, Weierstrass's theorems on constrained maxima, Jacobi determinant identities underlying Le Chatelier reactions, etc., while still not resting on the same empirical foundations and certainties. What Samuelson was outlining in this description was the fact that he had a very, very specific program in his research agenda, which was to reshape economics in the mold of physics. And that's frankly one of the reasons why all of us economists, myself included, we all suffer from a psychological disorder that I call physics envy. We would love to have 3 laws that explain 99% of all economic behavior. In fact, we probably have 99 laws that explain maybe 3% of all behavior. And it's terribly frustrating to us. Now, it turns out that this physics approach to economics was tremendously successful. If you go through and look at the milestones that have been achieved over the last 5 decades, things like utility theory, real preference, general equilibrium theory, game theory, macroeconometrics, portfolio theory, rational expectations, option pricing, and of course, the efficient markets hypothesis, all of those grew out of this particular research program. And it was very deliberate on Samuelson's part. Now, the focus that I'm going to take today is on efficient markets. We all, I think, understand what that is. Just by a show of hands, let me ask, how many people have been exposed to the theory of efficient markets? Which is most everybody. How many people actually believe the efficient markets hypothesis? Wow. I guess my work is done. We can conclude early. Now, I'm going to make the opposite argument, which is many of you should be raising your hands, which may be a kind of a surprise given the topic of my lectures. But I'll come back to that in a little bit. So it turns out that the efficient markets hypothesis was a real breakthrough in the sense that it provided very, very sharp implications about how prices should behave. And this is not that different from Adam Smith's invisible hand, or more popularly, the notion of wisdom of crowds. The fact is that even though none of us have all the information, the fact is each of us has disparate pieces of information which, when we come together and put them into the pot that we call the market, what emerges and it is an incredibly informed number. And that number has certain statistical properties, not to mention economic properties, that we now know and over time have tested and in many cases have rejected. So the behavioral critique that I'm referring to is, on the one hand, early statistical work that Craig McKinley and I have done testing the random walk hypothesis, which is a very special case of efficient markets, but also the body of literature that's emerged from the psychologists and behavioral economists that have demonstrated a variety of so-called behavioral biases, things like loss aversion, anchoring, framing, probability matching, overconfidence, overreaction, and so on. Many years ago, I spent a summer going through this literature, and by the end of the summer, I was just convinced that the human animal was the stupidest creature on earth. Because we all suffer from these biases. And I'm going to show you a very simple example in the next slide of such a bias. The fact is that time and time again, over the course of the last 3 decades, we've been able to document departures from all of the axiomatic assumptions that give rise to efficient markets and rational expectations. And for an economist, that's very, very frustrating because we know and love this theory of rationality and efficiency. It really is at the heart of virtually everything that we do and all that we teach, certainly in finance. So it's a bit surprising that none of you raised your hand about the efficient markets hypothesis, because if you're a student in an MBA curriculum, you do know that the core of what you learn in introductory finance and all of the subsequent courses are built upon the efficient markets hypothesis. That should give you cause for concern that what you're learning is in some sense defective, and that when you go out in your career and you try to apply your trade, you might be in for a rude awakening. So we're going to come back to that as well. So let me talk about the one example of irrationality and behavioral bias that I think most of you may not have come into contact with, because it's a rather old phenomenon that you really don't see in a lot of behavioral finance texts, and that's probability matching. Let me describe to you quickly what this anomaly is. Suppose that we play a game where I have a coin, and it's my coin. I toss it a series of times, and you try to guess which is going to come up, heads or tails. And if you guess correctly, I will pay you $1. And if you guess incorrectly, you pay me the $1. Okay? And we're going to do this many times. It's repeated over and over again. So I'll tell you right now that this coin might be biased. It's my coin, so I get to choose it. And for the sake of argument, let's suppose it is biased. Let's suppose that it's 75% heads, 25% tails. It's weighted towards heads. Now, you don't know this in advance. All you know is that it could be biased. So after we play for, I don't know, 10 or 20 trials, you notice that the relative frequency of heads is actually much, much greater than the relative frequency of tails. So what should you do? What is your strategy as an efficient markets, selfish, optimizing, rational economist? What would you do? Anybody? Heads. Guess heads all the time, right? The optimal strategy, profit maximizing strategy, should be to guess heads all the time. Well, it turns out that when you do this with subjects in a laboratory, they don't do this. They don't guess heads all the time. What they do, oddly enough, is that they seem to randomize, and they randomize heads versus tails with approximately the same relative frequency as the actual coin tosses. And what's even more puzzling, if in the midst of this you somehow switch coins surreptitiously, and instead of a 75-25 coin, you switch it for a 60-40 coin, then after another 20 or 30 trials, the subject will change his or her behavior and will then match that frequency as well, 60-40. Very strange, right? Now, you might think this is a minor little anomaly, but it actually had some pretty significant consequences in at least one context. Now, this may be an apocryphal story. I'll tell you up front, I haven't been able to verify it. I heard this story from my colleague Steve Ross, who claims that he heard it from Amos Tversky, the famous Stanford psychologist who died several years ago. So I haven't been able to verify with Tversky that this is in fact the case. But here's the story. The story is that during World War II, the United States had a number of bombing missions over Germany. And before the pilots got on board their bomber missions, they were given a choice. They could either wear a protective flak jacket that would protect them from shrapnel from air-to-air bullets that would strafe the sides of these fighters, these bombers, or they could pick a parachute that would help them in case they got shot down by a surface-to-air missile. Because in those days, the material that was used to make these protective devices was so heavy, made out of very heavy canvas with lead sewn in for the flak jackets, you actually couldn't wear both. You had to pick one or the other. And so it turns out that if you were going to get killed, the probability of getting killed by shrapnel was about 75%, and the probability of getting killed by being shot down by surface-to-air missiles was about 25%. So what do you think the pilots did? Now, it turns out that because all of these missions were volunteer missions, they felt that they had to let the pilots choose one or the other. So before they got on the plane, they had a table that had parachutes and another table right next to it that had these flak jackets. And the Air Force wanted to impose a requirement that they wear only one of the two. But the pilots protested. And again, because it was a volunteer mission, the Air Force had no choice but to allow them to choose. So what do you think they should have chosen in order to maximize their safety? Flak jacket all the time. In fact, what they did was that they picked the flak jacket 75% of the time, and they picked the parachute 25% of the time. So this is a real phenomenon, and it's a serious one that had some important repercussions. What's even more puzzling is that we find this behavior in other animal species. It's found in ants, fish, pigeons, primates, virtually anything that can make a choice between A versus B, where you can construct a randomized experiment, you see probability matching going on. For example, with fish, some psychologists actually had an experiment where they had goldfish in an aquarium. And they would divide the aquarium into two sides, left and right, and they would choose which side to feed the goldfish, the left or the right. And they would randomize that with 75% left, 25% right. You would figure that all of the goldfish would always go to the left side. But in fact, they randomized. Very strange. So the question, of course, is why? The behavioral finance literature often stops here and simply says, how stupid, how irrational. But in order for us to really understand how to take this bias and incorporate it into our theories, we need to know why. It takes a theory to beat a theory. And these anomalies are not theories. So is it irrational, or is there something deeper going on? And what I'd like to talk with you about over the course of the next 3 lectures is what that theory is. Not only why, but what it means for financial markets. So what I'm going to try to do over the course of these 3 lectures is to reconcile the efficient markets hypothesis with behavioral finance and argue that actually neither of them is correct, but in a way, both of them apply. They just don't apply at the same time with the same force. In other words, they're opposite sides of the same coin. That is, behavioral biases are actually adaptive behaviors that have been taken out of their natural context. So in a few minutes, I'm going to actually show you the logic behind probability matching and describe a context in which it actually makes perfect sense. Not economic sense, but perfect behavioral sense. And while these behaviors might actually be suboptimal from the individual's selfish perspective, from the population's perspective, they are actually optimal in a very different sense, in the sense of maximizing growth. And of course, that's all we care about in biology. It's survival. Someone once said, I think it was Woody Allen, who said that 90% of success is just showing up. And I actually think that's an underestimate. So it's about survival, and that variation and natural selection shape survival in the same way that it shapes ecologies. And ultimately, the key to how behavior and the environment interact is really to determine the reproductive success of a particular behavior. So I'm using terms now that an ecologist or an evolutionary biologist would use quite intentionally. I'm not using it as an analogy. I'm using it in the exact sense in which biologists mean them. So this is not meant to be a kind of a metaphor for what's going on. It's actually meant to be an accurate scientific description of what actually happens. And I'll have to make that case over the course of the next 3 lectures. It's evolution applied to financial interactions, pure and simple. Now, let me give you a quick overview of the 3 lectures, just so you understand how things fit. I'm going to make a slight change in the order because of the nature of the exposition. Today, I'm going to give you a very brief introduction to the mathematical foundations of adaptive markets. I'm going to just derive the kind of analytics that you would need in order to understand how behavior evolves over time. So the key idea is how behavior interacts with the type of risk that affects reproductive success. And in particular, we're going to see that the notion of systematic risk and idiosyncratic risk, the ideas that were pioneered by Bill Sharp in the CAPM, actually play a critical role here, but in a completely different context. And that ultimately, it's really the difference between idiosyncratic risk and systematic risk that can explain a number of anomalies that we observe. They may be anomalous from an economic perspective, from the selfish optimizing perspective, but they actually make perfect sense from the biological perspective where you're looking at growth rates and you're looking at the thing that grows the fastest, because by definition, they're the ones that are going to be overrepresented in the population. This distinction between systematic and idiosyncratic risk can also explain both rationality and its departures, and ultimately it's going to provide us with the impetus to understand what bounded rationality means, and it'll give us a definition of intelligence, which is quite unexpected. Lecture 2, tomorrow, what I'm going to cover is the theory and practice of adaptive markets. So I'm going to spend some time talking about efficient markets as the frictionless ideal, but the reality as being many more frictions that affect our day-to-day interactions. And I'm going to draw on the cognitive neurosciences to do that. There's some really interesting evidence about what rationality really means from the perspective of the brain. And so we're going to bring some of that in. We'll talk a bit about some split brain studies that were done several decades ago that speak directly to this issue of how economists think versus how psychologists and other behavioralists think. And then I'll describe in explicit terms what I mean by bounded rationality and intelligence. And then ultimately, efficient markets can be interpreted as a departure, and behavioral departures as part of the same framework of that kind of cognitive neuroscience perspective. Then on Friday, lecture 3, I'm going to focus on a real live example of all of this theory and practice at work, which is hedge funds, which I call the Galapagos Islands of the financial industry. Because in the hedge fund world, you can see evolution happening before your very eyes. Unlike mutual funds and other slower-paced industries where it takes many years before you see real change, hedge funds are changing literally every year, and in some cases even more quickly than that. And so we're going to take a look at a very specific set of events that occurred in the hedge fund industry, in particular the quant meltdown of August 2007. And I'm going to hope to show you through a combination of empirical as well as institutional description that this notion of adaptive markets is actually occurring as we speak, and that we can use that to our benefit because hedge funds are the canary in the coal mine. They're the first to get hit with any kind of crisis, so we can look at them as a kind of an early warning indicator for systemic risk, and they're also the first to take advantage of new opportunities when they're created. Look through the lens of evolutionary biology and ecology, everything looks different. All aspects of economic interactions look different. So what I'm going to try to do over the next 3 days is to change your perspective. It's to broaden it by using this kind of evolutionary lens. And then from that point on, no matter what you look at, whether it's efficient markets or rational expectations or game theory or auction mechanism design, all of these things will look different now once you understand the totality of how human behavior can interact with economic interactions in institutions. So there's a large literature that I'm going to cover, and I'm not going to have time to refer to that. So this is my one slide that does the citation to the literature, and even this obviously doesn't do justice to it. There are many different fields that I touch upon in what I'm going to be discussing, things like, of course, behavioral finance and economics, but also psychology and the cognitive sciences, evolutionary psychology and sociobiology, evolutionary game theory and economics, and behavioral ecology and evolutionary biology. There'll be some very old concepts that I apply, but there'll also be some very new things that I do. And so I'm not going to have time to do a proper attribution to the literature, but of course the printed version of these lectures will have a full bibliography, and the papers that I cite, as well as my own papers on my website, you can take a look at the bibliography. We try to cite pretty much everybody that has been relevant for this, which means that our bibliography is almost as long as the paper itself. So, okay, with that as the introduction, I'm going to begin. And first, I want to apologize in advance for today's lecture. I'm going to be a little bit more technical than tomorrow's or Friday's. And I do this very, very deliberately because what I'm about to show you is a relatively simple model that has some rather remarkable conclusions. And so in order for you to fully appreciate those conclusions, you have to understand where they came from. And so using nothing more than high school mathematics, but it will be some involved calculations, I'm going to actually take you through how to derive the adaptive markets hypothesis, or at least versions of the behavioral results that we get. So I apologize for going through some of that. I know it's a bit boring, but it's actually important to see that in order for you to believe that the results are really true, since I'm going to be coming up with some rather surprising conclusions from a relatively simple model. And I'm aware that the rigor is not necessarily appreciated by all the attendees. Someone once reminded me that along with rigor usually goes mortis. So I want to be respectful of that. So let me first start with the model. And the model is the simplest possible model. In fact, if it were any simpler, it would be trivial. In fact, some people may think it is trivial even now. It's a binary choice model where I'm going to consider certain individuals that will be faced with a choice of A versus B. That's it. There are two choices. And each of these choices leads to consequences. In the biology literature, this would be called asexual semiparous individuals. What I mean by that is not, I'm not referring to MIT undergraduates. I'm referring to beings that make one decision in their lives and they give birth asexually and then they die. So that's it. It's just one round of reproduction. And so these individuals live for one period. They make a choice, A or B. That choice determines whether or not they get offspring X of A or offspring X of B. So X of A and X of B are just random numbers of offspring. Okay? That's it. And the only other assumption that I want to make is that the offspring of a particular individual behaves exactly like its parent. Now, what do I mean by behavior? Well, I'm going to parameterize behavior in a very simple way. These individuals will pick A versus B by tossing their own coin. And their own coin has a probability F of being A. Okay? So one of these individuals pulls out its coin, and the coin is got a probability F of coming up A and a probability 1 minus F of coming up B. And it tosses the coin and it gets a realization. And that's all that it does. Once an individual is labeled an F, it will remain an F, and therefore all of its children will be F types. Okay? Now F can be any number between 0 and 1, including 0 or 1. So you can have somebody who always chooses A in the population. In that case, its F would be F equal to 1. You can have somebody always picking B, and its F is equal to 0, and you can have anything in between. So you have all different types of Fs. Okay? And in order for us to understand the consequences of behavior, we have to say something about XA versus XB. And so what I'm going to do is to summarize all about the biology, all about the environment, all about how the interactions of the individual's decision-making impacts reproductive success with my assumption about the joint distribution of XA and XB. I'm going to simply assert that there's some probability distribution function phi of XA and XB. Okay? Now, recognize that this really reduces a lot of information that biologists, economists, ecologists care about. But I don't right now. All I want to know is if you choose A, what's that going to mean for you in terms of reproductive success? If you choose B, what is that going to mean for you in terms of reproductive success? And if that's all I care about, then all I need to know is this joint distribution, phi of xa and xb. Okay? It summarizes all the information that I need to know about behavior, about the methods of reproduction, about genetics. Everything is contained. So you can think of it as a biological reduced form, to borrow a phrase from macroeconomists. This is not a structural equation that tells you how reproduction works or how the environment affects the individual. All it says is if you pick A, you get a certain outcome. If you pick B, you get another outcome. And it's parameterized by this probability distribution. Okay. Now, this experiment that I just described is going to be repeated for many generations. So you'll start out with one particular F. The F will reproduce asexually. It'll just generate offspring based on a choice. And that offspring will generate its offspring based upon that same coin with a probability F. And after a while, you'll get a bunch of individuals of type F. So the thought experiment that I want to do is to start with an initial population of all possible types of F from 0 to 1. We have all types in our little population. And we'll let them reproduce. And as they reproduce, we will see which kind of F emerges as the most popular F. Now, in this little depiction of this multiple generational trial, you can see that there is one F that dominates, which is the green F, F4. That's the type that dominates. And so if we can identify the type of F that dominates, that's the kind of behavior that survives. That is the behavior from an evolutionary perspective is selected. Natural selection will determine that that behavior is the one that is reproductively most successful. Okay? Any questions? That's it. That's the model. That's the whole model. As I told you, it's about as simple as you can get without being totally trivial, right? Now, at this level, you might not think you could say a whole lot. But you'd be actually surprised at how sharp a set of conclusions come out of this very simple framework. So let me describe to you what kind of conclusions come out. In order to derive conclusions, we have to say something about that randomness. So here's the simplest possible assumption that I could assert for that distribution function phi of xa and xb. I'm going to assume that the distribution is identical across individuals of a given generation, and that it's independently and identically distributed over multiple generations. So let me explain what that means before we go on. When I say that it's identical within a given generation, if you and I are in the same generation and you pick A and I pick A, we will both get the same random variable xa. Not the same distribution, literally the same realization. We get the same draw. So if xa as a random variable ends up being 3 in one generation, if you pick A, you get 3. If I pick A, I get 3. Okay? Now, I could have alternatively assumed that we get the same statistical distribution, but they're independent. So in other words, if you pick A, you get a distribution xa, and I get A, I pick the same distribution, but your draw 3 could be different from my draw 4 in any given generation. They're drawn from the same distribution, but they're different draws. I'll assume that later. For now, I'm assuming that it's the identical draw. The way that ecologists would phrase it, you and I are part of the same micro niche. That means that we are subject to the same realizations of the environmental factors that determine the outcome of our choices. Over time, across generations, the distribution is identical and independently and identically distributed, meaning that your children, if they pick A, they get XA. The realization of your children's XA is different from your realization of XA. It's independent, okay? And finally, your choice, which is indicated by this indicator function, I, that's a 0-1 variable that indicates whether you pick A or B. That choice is statistically independent from everything else. So in other words, what we're modeling is mindless behavior. All of these creatures are tossing their coins with different Fs, statistically independently from outcomes and from everything else. Okay, so I want to emphasize once again that we're talking about mindless behavior. There's no rationality or irrationality. It's just creatures choosing A versus B. And I also want to mention that this theory applies not just to humans, but it applies to anything that can choose A versus B. It can apply to bacteria, to single-celled organisms that choose between high concentration of sodium or low concentration of sodium, or they choose swimming left or swimming right. It's any creatures that have a choice. And what we're going to do is to calculate which of the different F's between 0 and 1 is maximized. That's the one that you will see in the population after multiple generations. According to Ernst Mayr, the evolutionary biologist, evolution is the process of elimination. That's what we're trying to see. Which of the behaviors get eliminated, get cast by the wayside, and which of the behaviors will persist. So to do that, all we need to do is to figure out the F star that maximizes the growth rate of its population. Okay? How do we do that? Well, it turns out it's pretty simple. And because of the time constraint, I'm not going to have time to go through the mathematics, but basic population arithmetic, if you go through and calculate the number of individuals of type F in generation T, you can actually show that using the law of large numbers, there's a bottom line conclusion, which is that the growth rate of a particular type, F, is given by this very simple expression. The expectation of the logarithm of F times XA plus 1 minus F times XB. That's it. That's the most difficult part of the mathematical derivations in this analysis. It's simply applying the law of large numbers to the data of the number of individuals in a particular population. This is the geometric growth rate of type F individuals. And so all we need to do is to maximize this function as a function of F to get F star. And that will tell us what kind of behavior grows the fastest in this very, very simple population. Well, it turns out that it's actually not that hard to do this. Again, high school maths is all you need. First of all, you observe that this function is globally concave. You take the second derivative, it's always negative, which means that it's got a unique maximum. And a concave function has only 3 possibilities for where that maximum is going to be. If the function looks like this, then the maximum occurs here when F star is equal to 0, right? If the function looks like this, then the maximum occurs at this endpoint where F star equals 1. And if the function looks like this, then the maximum occurs somewhere in the interior where F star is strictly in between 0 and 1. So let me just explain to you what the implications are. What this means is that when F star is equal to 1, it means that this individual will always choose A, always. You'll pick A 100% of the time. And its children will always pick A 100% of the time, and so on and so forth. Similarly, if F star is equal to 0, then that type will always pick B 100% of the time, and its children will pick B 100% of the time. The weird case is where F star is in between 0 and 1. This is a case where you randomize. And that's counterintuitive from an economist's perspective, because why would you choose to randomize? Now, game theory has certain examples of mixed strategies, so that's certainly not new to economics. But in a simple context of utility maximization where there's no strategic interactions going on, it seems a little odd. Now, it turns out that you can actually solve for F star in this simple case. And let me just show you intuitively what the solution is, and then I'll go through an example and try to wrap up. F star is equal to 1 when these 2 conditions hold. These 2 conditions say that the expectation of the number of offspring if you pick A divided by the number of offspring if you pick B, if that ratio is greater than 1 and the ratio of the reciprocal has expectation less than 1, when those 2 conditions hold, then you should always pick A 100% of the time, because that's telling you that A is much better than B in terms of number of offspring. Similarly, if you look at the third line, if the expectation of XA over XB is less than 1 and the expectation of the reciprocal is greater than 1, you should always pick B 100% of the time. But in the middle is where things get really interesting. If the ratio of XA to XB has expectation greater than or equal to 1, and its reciprocal is also greater than or equal to 1 in expectation, then you randomize. And the randomization is given by the solution to this equation. And if I rewrite it this way, you might find it more intuitive. What this last line says is the expected ratio of the offspring you get from picking A divided by the average offspring better be equalized to the expected number of offspring if you pick B over the average offspring. You can think of it as a kind of an Euler equation that is trying to balance the benefits of picking A versus B. Now, how does F star persist? Let me just give you one kind of intuition about this. F star persists in the sense that if you take any other F behavior, when you take the ratio of the number of F prime types divided by the F star types, it turns out that that ratio converges to 0 infinitely fast. It exponentially fast. This is the sense in which F star is the behavior that we observe after many, many generations under this very, very simple setting. Now, I want to skip ahead because I want to just illustrate to you what this means in a very simple example. Suppose that the distribution phi of xa at xb is itself binomial, so Bernoulli trials. So there are two states of the world, state 1 and state 2. And so xa, if you pick A, xa is equal to m offspring in state of the world 1 and nothing in state of the world 2. But if you pick B, then it's exactly the reverse. Then the number of offspring, if you pick B in state 1 is 0 and m in state 2. Okay? And let's say the probability of state 1 occurring is p and the probability of state 2 occurring is 1 minus p. If you take that very simple description of phi of xa at xb and plug it into the expression and solve, guess what F star is? F star is equal to p. F star is exactly equal to the probability of state 1, probability matching. Now, if you're like me, when you first come upon this, it's hard to understand or interpret. So let me translate it for you into an experiment that I understood, because from an ecological perspective, it was much more intuitive. I want you to imagine a really simple ecology where there are two states of the world. It's either sunny or rainy. And you are a creature in this ecology. You are trying to decide where to build your nest. So you have only one decision, which is where to build that nest. You have two choices of where to build it. So it's either sunny or rainy with 75% probability or 25% probability. And you have two choices to build your nest. You can build your nest in the valley where there's water, or on the top of the plateau where there isn't any. Now, if you build your nest in the valley and it happens to be sunny, that's wonderful, because there's water in the river in the valley, and the valley provides shade from the rays of the sun. So your offspring will survive, and you'll be reproductively successful. However, if you build your nest in the valley and it rains, the river will flood, drowning your offspring. You will be unsuccessful. So what you're looking at is offspring of 3 if it's sunny and you build your nest in the valley, and extinction if you build your nest in the valley and it happens to rain. If you build your nest on the plateau, it's exactly the reverse. Why? Because if you build your nest on the plateau and it's sunny, the rays of the sun will burn your offspring to death. Then there's no water, so they'll either burn from the rays of the sun or they'll die of thirst. If, on the other hand, it rains and you're on the plateau, there's water, and the clouds are protecting your offspring from the rays of the sun, so your offspring will survive. So this is the simple choice you're confronted with. As an optimizing, expected utility maximizing, selfish, intelligent, rational economist, what should you do? You should build your nest in the valley 100% of the time, right? Always build your nest in the valley. Well, let's suppose you do that. How would you compare to somebody who randomizes? Let's see. We know the answer mathematically, but I actually discovered something interesting. When you talk to biologists, they're actually quite suspicious of mathematics. They want to see a simulation, and which is fine with me as an econometrician. I definitely appreciate simulation, but actually I thought the closed form solution was neater. But here's a simulation of what happens. So I've got a bunch of different creatures with different Fs. F of 0.2, 0.5, 0.75, which is the probability of sunshine, 0.9, and then f equal to 1. That's the economists in the right-hand column, right? Let's do a simulation and see what happens. So here we go. The economists are growing faster than everybody else. Not surprisingly, they're going faster, 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 faster until, whoops, something happened. What happened to the economists? Well, it rained. The first time it rains, they're wiped out. That behavior, purely selfish, optimizing, rational behavior, can't persist because all of the economists are in the same boat, the boat that will sink when it rains. They are not diversified, whereas the populations that have randomizing behavior, they are diversified. And diversification works beautifully when it's actually done in tune with the probability of rain or shine. When you equalize the probability, what you're doing is you're equalizing the expected return in the two different states of the world. That's the one that's going to maximize your population regardless of whether it rains or shines. That's what you ought to be doing if you are trying to maximize growth. Now, of course, none of us is trying to do anything. This is mindless behavior. Nature is maximizing growth. It's the winners that get to write the history, the survivors that write the history. So this is an example of probability matching explained, and in some additional research that we've done, we've actually not only explained probability matching, but in the more general case where you don't have such extreme outcomes, we actually can derive non-probability matching behavior. In fact, we can also derive purely selfish behavior as well, depending on the environment. The key is it depends on the environment. So let me skip ahead because I want to conclude with some observations about where all of this fits. And that is, if you change one simple assumption, using this framework that I just described, the kind of anomalies we can explain are probability matching, randomization, risk aversion, risk-sensitive foraging behavior, loss aversion, anchoring, framing, a lot of the behavioral biases that the psychologists have documented, we can explain in this totally simple, mindless framework. Not to say that this is the truth, but rather that in such a stripped-down version, if you can explain these basic phenomenon, there may be some very deep underlying reasons why they exist. And tomorrow we're going to have to examine some of the neuroscientific evidence for where these kinds of circuits lie in the brain. But the last thing I want to talk about today before concluding is that what if it's the case that we make one very slight change in the assumptions that I made? And I didn't make that many assumptions, but the one assumption that I want to change is what if it's the case that this kind of identical distribution assumption, what if we change that from being identical to being independently and identically distributed? So in other words, you and I, we are now no longer part of the same microclimate. We are part of the same statistical distribution, but your draw is independent from my draw. Now remember, the economists in the previous example, they all got the same draw, which means that when it rained and they put their children in the valley, all of their children got wiped out. It's because they all had the same outcome because it's the same distribution. I now want to change that. If I make that one slight change, I now assume that we're IID as opposed to independent. It turns out that all the results that I just derived for you disappear. The results, the mathematical framework is still correct, but the conclusion is completely different. When you do the analysis with idiosyncratic reproductive risk, if it's idiosyncratic reproductive risk, then guess what? When you do the optimization and you do the mathematics and you go through and you apply the law of large numbers, it turns out that what you get is no longer stochastic, and therefore the optimization turns out to be 100% of the time always pick the valley. There is no randomization. You don't need to do any randomization. The reason you don't need to do any randomization is that the probability that all of us doing the selfish thing, if we all pick the valley, the probability that all of us will get drowned is 0 because we are all under our own little microclimates by assumption. So if you do the simulation now, what you observe is a very different outcome. In fact, now the economists dominate. They are fruitful and they multiply faster than anybody else, precisely because they are already diversified, thanks to my assumption of idiosyncratic risk. So the conclusion of this very, very simple model is that idiosyncratic and systematic risk have very different implications for reproductive success, and therefore for behavior itself. And so when we start thinking about the CAPM, we have a new appreciation for why systematic risk is such an important role in thinking about asset pricing. There are many extensions of this model that I won't have time to talk about, but you can read about that in the papers. We can derive punctuated equilibrium from regime switching models. We can get group selection by imposing factor structure on XA versus XB. And if you impose memory and conditioning information, you actually can get forward thinking and planning behavior. In other words, you can actually derive rational expectations from a very simple evolutionary model. In fact, tomorrow, I'm going to describe to you how it is that bounded rationality comes out of this model if you impose resource constraints, because we haven't so far. So let me conclude here by saying that this mathematical framework provides a very, very simple way to evaluate behavior in the context of random outcomes and random environments. And that really, it allows us to subsume a lot of the detailed structure of economic relationships and environments into a way that even an econometrician like me can understand. It really compacts information and allows us to get to the bottom line, which is what behaviors survive and what behaviors do not. The simplicity of this model, we think, is actually a feature, not a bug. We think that it's so simple and stripped down, which means that there are very few moving parts and very few things that one could object to, because there's just not that many complexities. As you layer complexity into the model, you can generate much more sophisticated behavior. But even at this very simple level, what we get is behavior that's surprisingly rich and with great explanatory power. And finally, it provides the mathematical basis for what I'm going to be talking about for the next 2 or 3 days. I'm not going to go through the mathematics. This is really the extent of it. And as you see, it's not that complicated, but it does require some detailed calculations. What it gives us, though, is license to expand the domain of evolutionary biology to economic behavior. And when we do that, everything changes. So I hope that you'll come back tomorrow and Friday to see what the implications are. And at that point, I can provide you with some more detailed justification, both on the biological side as well as on the economic side. Thank you.